All right, so just like you see right here, it says acids are substances that surround us in everyday life. The uses of acids range from providing essential nutrients for our bodies to dissolving metals. Some acids are safe to handle with our bare hands or even used in food preparation. Other acids are going to severely burn human skin. It's important to understand how these substances can all be acids yet have such different properties. Okay, so we're going to really be focusing in on acid strength and conductivity. However, I do want to point out that bases are pretty similar in the sense of knowing whether they are strong or weak, okay? Because it's all going to have to do with conductivity and being strong electrolytes, all right? So I think that was one of the properties that you guys got to see on your first assignment on Monday, learning about the basics of acids and bases, right? So electrolytes, they were both electrolytes. Strong acids, strong bases are both strong, strong electrolytes, meaning they conduct electricity. So, but we're going to focus in on acids because this is a really good picture to kind of get my point across here. So what we see here is we have something like hydrochloric acid versus hydrofluoric acid. Now, if we were to look at a periodic table, we would see that these are both, fluorine and chlorine are both in group 17. However, what we would notice is that on the periodic table, fluorine is up here, chlorine is next, right? So fluorine was up in that highly electronegative corner, meaning that it holds on to things. It attracts those electrons. So basically, fluorine is going to hold on to hydrogen very, very tight. This one, it's pretty electronegative, but it's not holding on as tight. And so what we see here in the difference in these two pictures is they both kind of start out with the same amount, right? So, and they look very similar. What these are water molecules in this first beaker. And what we're showing is if I pour hydrofluoric acid into that, or if I pour hydrochloric acid into that, this is what we're looking at, okay? So the obvious thing that I'm going to point out is that the good electricity, conductivity. There we go. All right, so the fact that this is conducting electricity a whole lot better. You can see it by the lights being very bright, right? Versus this is showing that a weak acid is not going to be conducting that electricity. Okay, so let's look a little bit deeper. Let's look into these pictures, and what you end up seeing is you have these funny little things forming, right? You have H3O, okay? So H3O. What that means is you have an oxygen with 3 hydrogens attached, which tells us that we have 1 extra hydrogen, right? And remember, hydrogens, those are the things that kind of tell us we have an acid, right? So this is called hydronium. And so what these different hydroniums are showing is that we have that extra hydrogen, meaning it's more acidic. So if we were to sit here and count, we would say, oh, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 hydroniums, okay? I'm going to put H+. Down here, you can see that we only have 1, 2, 2. So we have 2 hydroniums, okay? The reason why is basically right here, these little hydrofluoric acid molecules, that fluorine is holding on tight to that hydrogen. It's not separating. So as you can see, you have a lot of those hydrofluoric acid molecules just kind of floating around, right? Only 2 of them let go to create those hydroniums. So a weak acid is all about does not ionize. The special word is ionize. Another way to say that is it doesn't dissociate. It doesn't split. So HF kind of stays put, stays together. It does not turn into H plus F. It only does that for a couple of these. Whereas if you look at hydrochloric acid, right, so we have our HCl, that one ionizes 100%. Okay, so it turns into H plus and Cl minuses, and those H pluses are becoming those hydroniums. Okay, so the fact that this is a 100% versus, we'll call this a 20%, that's what we're looking at. How much does it ionize? Okay, so strong acids ionize completely, weak acids ionize partially, and that's going to be our focus. Now, chances of us asking you guys to explain that back to us, not very likely, but we do want you to know partially, right? So partially ionizes versus completely ionizes. And that's what tells us that is a strong electrolyte versus a non-electrolyte, okay, or a weak electrolyte. So strong acids are going to be strong electrolytes. They are going to conduct electricity, so you're going to see that. So conductivity is going to be high. That's going to be on one of your questions today, okay? And you're going to see that they completely ionize. So we're going to look at, and this is actually goes for also your strong bases, okay? So they completely ionize, meaning they're strong electrolytes. Your weak acids and bases, okay, so your weak acids and weak bases are weak or non-electrolytes. Usually they're weak. Okay, so conductivity is going to be low, and they partially ionize. Sorry to write over the words. But that's the definitions that we need to know about weak versus strong. Now, what we are going to ask you guys to be able to do is to remember your strong ones, okay? Because here's the rule. If it's not strong, so I'm going to put this right here, not strong, then you're weak. Okay, so if you are not part of the list of the strong acids or the strong bases, then you are considered a weak acid or a weak base. So that kind of keeps it simple because there's only 7 that we need to know, and there's only 8 of the bases. So let's talk about the acids first. So super simple. For binary, remember that means we have 2 elements. There are 3 that are considered strong. We have a little sentence that we tell you guys. It's I bring clay. Okay, I bring clay. And what this represents is iodine, bromine, and chlorine. Anytime we have those hooked up with a hydrogen, they all have a -1 charge. Okay, just like this. These are binary acids. All of these are considered our 3 strong binary acids. They're all coming from group 17. If you notice, we did not include hydrofluoric acid. That's because what we just saw in our last slide is that hydrofluoric acid holds on to its hydrogen. So it doesn't, it only partially ionizes. That's why we leave that one off. Okay, so these are your 3 binary strong acids that we expect you to know. So again, I bring clay. Sometimes we say not food, okay? All right, your ternary acids, there's an easy way to do this. You remember one rule, and that is that if it has 2 or more oxygens than hydrogens. Okay, so if it has 2 or more oxygens than hydrogens, it is considered strong. If it does not, that is weak. So for example, if I have something like nitric acid, okay, so here's my nitrate. It ends with 8, so I change it to nitric acid, and there's my hydrogen. Okay, but looking here, looking at this little ratio, if it has 2 or more oxygens than hydrogens. So we have 3 oxygens, we have 1 hydrogen. That's 2. That's a strong acid. The scary one that lots of people are like, ooh, that sounds scary, right? So phosphoric acid, that would be phosphate. We're going to have that -3 charge. We have hydrogen with that +1. We crisscross them. You end up with H3PO4. H3PO4. Now let's look at this little 2 or more oxygens. It has 4 oxygens, 3 hydrogens. That means it's only 1. That is not a strong acid. So it looks scary, but it is not a strong acid. Now, just so you know where that's coming from. So remember, big idea, it has to completely ionize. It has to completely split like this. Okay, when you have something like nitric acid versus phosphoric acid, what you're looking at here is you have your little nitrogen. We have 3 oxygens. These guys are all pulling away from this little hydrogen. So this is most likely going to break this little bond right here, and it's going to ionize. Now, over here with our H3PO4, we have 3 H's, a P in the middle, and we have the 1, 2, 3, 4. If you look at this and you were to think of it like a tug-of-war game, 4 against 3, it's going to be a pretty boring match. You're not really going to be pulling as hard as something like 3 versus 1. So that's what makes this not a strong acid, but this is. It's It's about completely ionizing. All right, so one more time. I bring clay. Those are your 3 strong binary acids. Ternary acids, so anytime you have your polyatomics, you're looking at 2 or more oxygens and hydrogens, okay? And there are 4 of those. So you can kind of look through your little list of polyatomics and see them, but H2SO4, so sulfuric is one, nitric is another one, chloric acid, and I believe perchloric acid. 1, 2, 3, 4. There they are. Okay, so those are the 4 ternary ones that you can just, if you want to just memorize it, go for it. And then you have your 3 binary ones right here. All right, the other one we got to know is our bases. So there are 8 of those. This is really simple. You have a periodic table. What you're going to do on that periodic table is you're going to draw a big B for bases. And any of those that fall in that B and they are attached to a hydroxide is going to be considered strong. So we're going to start at lithium. We're going to draw our line down to cesium, over to barium, and up to calcium. All right. Any of these attached to a hydroxide is going to be your strong base. Anything else is weak, okay? These guys are going to let go. They dissociate. They completely ionize. Anything else is holding on just a little bit more because you're heading more to the right of your periodic table, which tells you that they're a little more electronegative, okay? So it's all about letting go. You want the ones that let go, right? So like I said, any of these attached to OH. So just to kind of remind you about crisscrossing your charges, that means that we have lithium hydroxide. This is a +1, -1, so no subscripts here. Same thing with everybody from group 1. So NaOH, KOH, or BOH, and CSOH. Okay, once we get to group 2, though, we have 3 in that little category. Now we're dealing with a calcium that has a +2. OH still has that -1. We crisscross those, we end up with CaOH2. That means, oops, did not mean to put that in the parentheses, but OH2. That means our next one's strontium, so we have SrOH with a 2, and then BaOH with a 2. Okay. All right. I'm also going to take a second to remind you that anytime we have these transition metals, you're going to see it written. For example, if I give you something like iron 3, so I'm going to give you 3 lines. So iron 3 hydroxide, you have to cross your charges. This 3 is the charge. So you would basically write this Fe, getting that from right here. There is not a guaranteed charge, right? It's not one of our +1, +2, +3s. It's not none of those. But if I have a 3 right here, that's telling me it's a +3 up here. Hydroxide is still that -1. Crisscross those, we end up with FeOH with a 3 on the outside. So don't forget to crisscross charges with these bases. All right, so once again, strong bases, we make a B on our periodic table. Anytime they're attached to an OH, that makes them a strong. Anything else, weak. So this iron 3 hydroxide, weak. All right, hopefully that helps.